Welcome to our comprehensive review on carbapenemases. We will explore their classification, epidemic clones, One Health drivers, diagnostic frameworks, and mechanism-directed therapeutics. Carbapenemases pose a critical global health threat by inactivating nearly all beta-lactam antibiotics, including carbapenems. These enzymes have spread internationally, affecting Enterobacterales, Pseudomonas aeruginosa, and Acinetobacter baumannii. The World Health Organization classifies these as critical priority pathogens. In 2019, over 200,000 deaths were linked to carbapenem-resistant infections, with high mortality rates in intensive care unit settings. Welcome to Chapter 1, Classification. We'll explore the Ambler and Bush-Jacobi frameworks for carbapenemase classification, crucial for guiding diagnostic and therapeutic strategies. Carbapenemases are categorized into three major classes: Class A serine carbapenemases, Class B metallo-β-lactamases, and Class D OXA-type enzymes. Class A uses serine for hydrolysis, Class B relies on zinc, and Class D is known for oxacillin hydrolysis. Understanding these classes is crucial for diagnostics and treatment strategies. Of note, azetrionam is not hydrolyzed by Class B enzymes. Isn't that cool? Let's explore 5 dominant carbapenemase families. KPC, first detected in the United States of America in 1996, is a major global driver. NDM, identified in 2008, spreads via a unique lipid anchor. VIM and IMP are key Class B MBLs, with VIM2 prevalent in P. aeruginosa. OXA-48-like enzymes originated from Shigella species, spreading via INC-L/M plasmids. Carbapenemase dissemination is propelled by a few highly successful bacterial lineages. These epidemic clones repeatedly acquire, stabilize, and propagate resistance genes, significantly contributing to global spread. Their success is not solely due to mobile genetic elements, but also their ability to adapt and thrive in various environments. High-risk clones exhibit immune evasion via capsule locus variation, high plasmid uptake, and adaptability in healthcare and community settings. Notably, ST11K pneumoniae strains in China now carry hypervirulence plasmids with carbapenemases, posing a severe antimicrobial resistance threat. Carbapenemase-producing organisms, CPOs, show varied regional distribution. Asia-Pacific has the highest rates, with significant resistance in South Asia. Europe shows a north-south gradient, while the Americas see Klebsiella pneumoniae carbapenemase dominance. Africa and the Middle East face high burdens, and Oceania has lower rates. The coronavirus disease 2019 pandemic exacerbated global CPO spread. Carbapenemase dissemination is driven by interconnected reservoirs across human healthcare, community, animal, and environmental domains. These reservoirs extend beyond traditional hospital-based infection prevention, highlighting the complexity of controlling carbapenemase spread within the One Health framework. A 2011 survey revealed NDM-producing bacteria in 4% of drinking water and nearly 1/3 of seepage water samples in New Delhi. This highlights how environmental contamination perpetuates a cycle, re-entering human populations via direct contact, food, and water. Timely carbapenemase detection is crucial for infection control, appropriate therapy, and surveillance. The diagnostic toolkit includes phenotypic assays, rapid lateral flow immunoassays, molecular platforms, and whole genome sequencing, each serving distinct roles in identifying and managing outbreaks effectively. Phenotypic methods like modified carbapenem inactivation method offer high sensitivity and low cost, ideal for resource-limited settings. Lateral flow immunoassays, such as NG-test Carba5, provide rapid results but have limited target coverage. Molecular methods, including polymerase chain reaction and whole genome sequencing, offer comprehensive detection and support outbreak investigations. Early identification of enzymes like Klebsiella pneumoniae carbapenemase, New Delhi metallo-β-lactamase, and oxacilinase 48 is crucial for effective therapy. The advent of novel beta-lactam/beta-lactamase inhibitor combinations has revolutionized carbapenemase-producing organism infection management. Treatment now hinges on identifying the carbapenemase class. Using a serine carbapenemase agent against a metallo-β-lactamase producer is ineffective, and vice versa. This mechanism-directed therapy marks a new paradigm in treatment strategies. For KPC and OXA-48-like producers, use ceftazidime-avibactam or meropenem-vaborbactam if susceptible. Imipenem-relebactam is another KPC option. For metallo-β-lactamase producers, aztreonam-avibactam is first line, supported by Phase 3 data. Sulbactam-durlobactam plus imipenem is preferred for carbapenem-resistant Acinetobacter baumannii, with cefiderocol reserved for refractory cases. Cefepime-taniborbactam shows promise against KPC, OXA-48, and metallo-β-lactamase producers, with Phase 3 results supporting Food and Drug Administration submission. Cefepime-enmetazobactam is approved in Europe for complicated urinary tract infections and pneumonia. Ceftabutin-ledaborbactam offers an oral option for carbapenemase-producing Enterobacteriaceae infections. Zeroborbactam plus cefiderocol targets serine beta-lactamases and metallo-β-lactamases. Non-traditional approaches include phage therapy, monoclonal antibodies, and clustered regularly interspaced short palindromic repeats-based antibacterials. Do not forget cefepime-zidibactam, which is a novel, newly FDA-approved, broad-spectrum antibiotic combination, often marketed as Zanich. It pairs cefepime, a fourth-generation cephalosporin, with zidibactam, a first-in-class beta-lactamase inhibitor that uniquely possesses intrinsic antibacterial properties. It is primarily used to treat complicated urinary tract infections and multidrug-resistant gram-negative bacteria. Therapeutic advances alone can't halt CPO spread. Core infection prevention and control bundles, including contact precautions and hand hygiene, are crucial. Environmental controls target biofilms and hospital plumbing. Antimicrobial stewardship, with carbapenem-sparing pathways and governance of new agents, complements these efforts. Whole genome sequencing and rapid diagnostics enhance outbreak investigation and infection prevention. Rapid diagnostics and mechanism-directed therapies are transforming CPO management. However, addressing the access gap in low- and middle-income countries is crucial. Integration of diagnostics, therapy, and stewardship within infection prevention frameworks is essential for equitable and effective containment of CPO spread globally.